So we did the first piece, which is the real basics of just how to work with this. Maybe you know what this thing is called? We have all kinds of graphs. You can call it, you can actually call it, the XY plane works, right? XY plane. You guys with me? Not a plane, you know, but you have a line, you have a point.
P-L-A-I-N.
P-L-A-N-E.
No, that's the airplane.
No, that's also the plane.
Oh, really?
Right, yes. Not the rain in Spain falls mainly on the plane. Not that kind of plane.
Oh.
Right. You have a point. You have an infinite number of points make a line. And then an infinite number of lines make a plane. So like this is a plane if you think about it going forever. You guys kind of with me? A little bit? Oh, you guys are like, I ain't listening to you at all. You gave me that quiz. Get over the quiz. Right? You make corrections, get over it. Get over it. Don't let that quiz, if you didn't do well in the quiz, don't let it get in the way of you understanding what the hell I'm talking about now. Get past it. Alright? So, that's called an XY plane. It's also called a rectangular coordinate system. Some of you guys might be aware there are like spherical or polar coordinate systems, so forth. I mean, this is where it gets really kind of neat. What's the main point about this system by itself? Just to be able to locate positions, right? Sort of like latitude, longitude on the Earth. With me? So to find a point, if this is the origin, let me say, like, you're the origin, right? So how do I get to you back there? I go one chair over, and then 1, 2, 3 chairs up, right? So you're at the point 1, 3. Are you guys with me? So I'm talking, you're the origin from my perspective, because I'm the most important person. So you're the origin, and then that's up, and that's down, and that's left and right. You guys semi with me? A little bit? So in this system, I move left, right, and then up, down, and I can locate any point on the entire infinite plane. Is everybody kind of cool with what I just said? I'm not going to do a lot of this. I just want to give you a little taste. Another way to find like that point is to start off at the origin, facing this way, right? Just imagine Jeff standing on this plane. I'm standing on it, right? So I'm facing this way, and you can tell me how many degrees to turn and then how far to walk. You guys kind of see what I'm saying? How can I get to that point? I can either go back and up, or I can go turn and then walk. And that's what's called polar coordinates. So there's a lot of different systems of how to find a position. And that sounds like, this shit's wrong with you people. Just pick one and stop. But the math is easier sometimes in another system. So we're just going to worry about XY plane, right? Yeah, I know I like to push it a little bit, but come on, I want to show you a little bit more about what this really gets to. So we did identifying points, we did plotting points. One thing I didn't talk about is, do you know what these regions are called? Quadrants, because there's 4 of them, so we call them quadrants. For some reason back in history, we decided to go anti-clockwise. This is 1, this is quadrant 2, this is quadrant 3, and this is quadrant 4. Just in case that comes up in the homework, those are quadrants, kind of makes sense. Broke it up into 4, sort of. All right, so here's where we kind of left off. We did problems like this earlier together on the board. So when I look at this, how many problems does this signify that I have to do? 4. Let me number them off for myself using good old Roman numerals. So if I want to do problem number 1, what does problem number 1 tell me? What do I? Yeah, I know x is 2, so I can use this relationship and replace x with 2. Oops, scheiße. No, you can't both be zoomed. One of you has to brightness. Okay. Now watch this. So here you get 4 minus y equals 3, right? Yes. Now watch. Now this is not always going to work. But this is right here. What's y gotta be? 4 minus what is 3? 1. So y is 1. You guys see that? I have no problem with you getting to this point going, well, y is freaking 1, Jeff. If you subtract 4, then you have to divide by -1. That's really easy to make negative mistakes. But right there, if you just take a step back and realize y is freaking 1. That's the only thing that works. Don't try that too often, and don't try that way at the beginning of a problem. No. Okay, so that goes right here. So this line is going to go through the point 2, 1. So anytime I have a collection of points that come from a relationship, from an equation, that means when I graph them, they have to have some kind of a shape to them. So if I have an equation where all my variables are to the first power, do you guys see that? X is to the first power, y is to the first power, is that cool? That's going to be linear. If x or y was squared, that would be parabolic somehow, either up and down or left and right. If they're cubed, then it really gets weird. Right? You guys semi with me here? No? Yeah, some of you guys still look like you want to beat me up, but all right. Okay, so what does this row 2 tell me I've got to do? Oh shit.
X is unknown.
Oh no, it's the matrix.
This thing is really crazy. What's that?
So
Yeah,
y
we went
is
to the matrix
3.
there for a minute. So I know that y is 3, but I don't know what the hell x is. Is everybody cool with this? Do you guys see this? Is this all right? I mean, that's really, it's a weird way to show it, but it is telling me that y is 3. And if I know y is 3, I have to be able to figure out what x is, because I know how they're related. So then what can I, just to solve this, I add 3. I can't, this is so poorly put together. Right? Divide by 2. I eventually catch up to it. So then it goes to the point 3, 3. I like it. You guys finish the last 2 if you haven't done that already. Oh, sure. Yeah, so where are we? Okay. So if you subtract 4, you're left with negative y. See that?
Yeah.
It's not y, it should be negative y, so then you have one more step to solve for y. Take the 4 away, the negative's still there. See that?
Yeah.
So it's negative y equals negative 1. Then you have to divide the list again. So that's what I'm saying. You can make a negative mistake real easy, but you can just look at it and you know it's gotta be 1.
I was just trying to
Oh, I got you.
understand
Verify.
more
I got
so
you.
than.
I'm with you. If I say this, then you'll lose like half your points for this piece. You see what I'm saying? If I say leave the table, you better do all 4. If I just say make your own table.
I got all 4.
Oh,
But I didn't.
oh, you have only plotted 2. That's fine.
The line.
I'm with you. That's all you need for the one. The thing is, you know, if you plot all 4, you can check to make sure they're all right. Because if one is off kilter, then yeah.
Why?
But if one's off your scale, then you definitely don't want to use that.
Why do the first 2?
But see what I mean? Or you made a mistake here. You could tell if your line, if you thought the point was here, you could tell it was wrong. Yeah, that's all. Yeah, to actually make a line, you just need 2 points. Agreed. All right, let me catch up to you guys. There. So the third one, I know that x is negative 1. So again, negative 2 minus y is 3, add 2. Negative y equals 5. Don't look up there, Jeff. Negative 1, y is negative 5. Is that right? No? What happened? Right? You plug a negative 1 in for x.
Okay.
Negative 2 minus y equals 3. Add 2.
Y equals y. The y is minus 1.
What do you mean? Sorry. What's?
The y is minus 1, right?
I don't know what the y is. What do you mean? It tells me here, it tells me x is negative 1. If I knew what the y was, it would be underneath
Yes,
the
I
y.
was.
Okay, okay. And then the fourth guy is these is 1 on here. It tells me that x is 0. For some reason, I get people do this, but what's still there?
Negative y.
Yeah, the negative, and then I got to kill it. Y is -3. Oh, I didn't put this in here. So this one is -5. This one is -3. So somebody just had a good point. You really only need 2 points to make a line. So you really could just pick 2 and put them down there, but to make sure that all your points are right, it's not a bad idea to do all of them, because they all have to follow the pattern that this sets up. So they all must be in a straight line. So 2, 1, 3, 3, -1, -5, and 0, -3. That looks good. Oh, that was the other class. I actually had a ruler in one of my classes. I don't trust myself with the trying to make a straight line. Oh, crappity do. Okay. That's supposed to. Oh, I'm good. Oh, okay, thank you. Somebody's like, you need help, sir. So what is this, when I make this line, what is that? How many answers are there to this? Infinite. Sometimes I have people say 4. That's 4 answers we found. But every point that I draw this line through, that point, whatever the shit that is, that point, whatever the shit that is, they all must work in the equation. Okay, like it. And that's the most basic reason we graph things, is because it's the quickest way to answer what are the answers. They're there. Right? Listing them all would take forever. Is everybody cool with this guy?
Yeah.
What's special about this point right there?
On one.
Is on the y-axis. So that would be where the line intercepts the y-axis. So remarkably enough, the creative geniuses that are math people, we said, let's call it the y-intercept. So that's the y-intercept. And I talked about this yesterday. The y-intercept happens when x is 0. You guys see that? When x is 0, I have to be on the y-axis somewhere. So when I made x 0, I found out that I was at -3. That's the y-intercept. So how do I find the x-intercept? I would have to make y 0. Let's see if you guys can go with me. What is it like? Somebody give me an estimate for what that looks like.
1.5.
1.5 is a good estimate, right? So let's see. If I make y 0, right? If I make y 0, I must be on the x-axis. I really want you guys, because y controls up and down. If it's 0, I am on the x-axis. I just got to solve for x to see where the shit I am. So to find the x-intercept, I make y 0. To find the y-intercept, I make x 0. In fact, just to really freak you out, my last math class, I had an equation with about 17 variables in it. To find the w-intercept, I made all the other letters 0. So that idea that I just said carries throughout all of mathematics. I think my last math course was Math 696. Yeah. And you're all like, whatever math course. Okay. Just trying to let you know that what you learn here extends throughout all of mathematics. So if I solve this, sure enough, I get 1.5, right? So that matches up with what it looks like it should do right there. Looks like it should be 1.5. Okay. All right. Not even joking about how much it looks like you want to murder me. Makes you laugh, so I'm just going to stop. So here, I want you to make your own table of values. In general, if I have to make my own table of values for something, I start with 0 for damn sure. I plug a 0 in for x, and then I plug like a -1 and a 1, and then you can pick one more number to throw in there, right? You don't want to, normally you don't want to put 80 in there. You see what I mean? So try to make your own table of values. Do you need a sheet? Oh, well, let me give you one now so you can do it. else need a copy? Alright.
As a y equal minus three x. That's
Yep.
always the
What do you mean? That's the equation. Y equals negative 3x plus 2. That's the equation. That's the relationship. You just pick a value for x, put it in, and then see what y is. So my suggestion was,
like that, we saw.
you can't solve it yet because you haven't put a value in for x. Pick one. So I'll do a problem. I definitely pick 0 for x first, or somewhere in there. So let's put a 0 in for x. What number could I put here? Just in general, I picked 0, but what could I have put there? Any freaking thing. You with me? Hey, I could have put 1.8772. Will I? No, because I don't want to, but I could, right? I can put whatever I want to into this equation. It will have some output for that. So I'm going to pick 0 because that's a beautiful number. It's going to kill that piece of the equation. So for this one, y equals negative 3 times 0 plus 2. So y equals 2, because negative 3 times 0 is 0. So I got a point. Now you guys try 1, negative 1, and then you get to pick whatever the hell you want for the last one. Anything you want. Except something you already did, right? First one, so like the second one, just in case you're still having some trouble, you could put a 1 in for x, so it'll be y equals negative 3 times 1 plus 2. Negative 3 plus 2 is negative 1. What's up?
How you got y equal
Say again, sorry?
How you got y equal
What's negative 3 times 0
0?
plus 2? Yeah. So you pick a value for x, you put it in, then you can simplify it, solve for y. Like it. So here, when I put a 1 in for x, I get a negative 1 for y. So now I just got to try, what about negative 1? And the last one, I'll let you guys use whatever number you want to. Yeah, what I want you to do, see how the scales are using it by 1. So here, that makes sense, you don't want to go by 1 for the x axis. Yeah, negative, or maybe positive. Yeah, you see that?
Yeah.
So you catch all the multiples of 5, but then your y-axis can be its own thing too, as long as you're consistent on that axis.
I used to do it.
Yeah, you do. Oh, so you put a negative 2 in for y. 2, 4. Yeah, 1 1/3, I like it. So 1 1/3. So you don't have to plot that, but when you do graph these over 3, you can see if it looks like, where does it hit negative 2 on the y? You can see what x should be 1 1/3, right? Okay. So plot these 3.
Okay, so this can be not equal number.
Yeah, of course, yeah, you have to catch every number in between all the numbers, yeah, because the line goes through every.
Professor,
Oh, I see. So just, if you do that and it's off of the scale I give you, just don't plot it. Because that's the other thing, you know, so that we were saying earlier, you really need to, yeah. All right, so let me see.
excuse me.
Oh,
Okay, why do you usually put the X?
where are we at? Sorry, what, wait, what's going on here? Okay. Oh, okay.
I lost you.
So here, it says x is one, right?
Okay.
So you replace x with one. So, why, I don't know why there's still an x there.
Yeah.
You're replacing x with one.
This is my question, why you don't put the X?
What do you mean? What are you talking about?
When you do it, you don't.
Because I'm replacing x with what it is. So, in the second row, x is one.
Yes.
So in place of x, I put one. That's why, because I already know what x is, so it's not an unknown anymore for that
Okay,
problem,
okay,
yes. So when you did negative one,
Put the next one.
right, you should have gotten 5, is that cool? Somebody tell me, what's a point you used here?
2,
6.
All right, so you used 2, what'd you get?
-4.
2, -4, let me see. So yes, you used 6, what'd you get for the output?
16.
-16, right?
Yeah, negative 16.
Okay.
0.5.
You used, wait, you used x, you used 0.5?
0.5.
So 0.5, yeah, okay. What'd you get out?
0.5.
0.5?
Yeah.
All right, let me see. Yeah, -1. Yeah. I'm with you. That was adventurous, I like that. Anybody else use the point they want to share or no?
I use a Y.
If I were you, I use 0.5 too, I got 0.5. All right, cool. So let's see. 0, 2, 1, -1, -1, 5. Right, so far so good. And then I can use 2, -4, that looks to be on track there, right? Let's see, 0.5, 0.5 looks good. See that? 0.5, 0.5. 6, -16 will be down here, that looks to be on track, right? But if you ever get a point that's off the scale, don't use it. You only need 2 points really. And then whatever the hell else you used, and let's see. Oh, somebody, that's right. Why does that not look right? You're in the wrong place. Make that bigger. Ah. All right, I like it. Just make those points bigger if it doesn't quite. We're humans, we make mistakes. All right, now this one, we haven't focused so much on the idea of scale yet. The scale I've been sort of giving you on these problems, right? Why do you keep doing that for me? Stop it. No! All right. So the x values look like they have to go by 5s. I don't want to use 1s, do I? 1, 2, do you want to go up to 30, -30 with 1 tick mark? 1, 2, 3, 4, 5, 6. I don't want to see that shit, right? So I can pick an appropriate scale for each axis. So for the x-axis, I definitely want to use 5s. 5, 10, 15, 20, 25, 30. Ah, 10, 15, 20, 25. What about for the y-axis? It looks like I probably just still use 1s. So I want you to really understand, you actually know this, you just don't really know it. As long as it's consistent on that axis, they don't have to have the same scale. So these can go by 5s, these can go by 1s. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Good job, Jeff. And then I can plot. Let's see, -30, 5. 15, 2. -25, -1. Pop. Okay. And no, I did not say they came from a line. They don't make any shape because they're just separate points. Don't try to connect them. Yes?
So we should try to, like, if it doesn't make a line, like, we shouldn't make a line or worry about that unless it tells us to, for sure.
If I give you any equation and that's where the points come from, they must make a shape. And if they all the variables have a first power, they must make a line.
Okay.
The minute those powers are different, they'll make a curve somehow. Yeah, I like it. If I just give you points from out of nowhere, they don't have to make a line. They could just be points I just thought of. I like it. Okay, so let me shut up for a while. Maybe if I shut up for a while, your anger will dissipate. I want to show you something kind of nifty. I found this a while back, and I know these guys have done some other videos, but I always go back to this one. My point in showing you this is not about darts, it's about the math, but if you like darts, you'll be that much more interested in this. Let me see, where's the volume? What's the volume doing? Let's see how this goes.
But I'm good at engineering, which means I'm actually really good at darts. Most of the projects I build for my YouTube channel take a month or two to pull off, but I've been working on this beast with my former NASA coworker John for over 3 freaking years, and here she finally is. It's fairly self-explanatory, but you throw a dart, and as long as your initial throw is somewhere within this diameter or so, the dartboard helps out a little bit. And what's cool is if you use this dart, it will make you the world's best dart player because you get a bullseye nearly every time. And even if you don't, it's really close. But if you use this dart, it makes you the world's worst dart player because it calculates the initial trajectory and then moves the board in the exact opposite direction. So eventually we took this thing to a bar to see if it would work in the wild. But before we get to that, let's talk about how it actually works. Fundamentally, there are 2 main parts to the system. First, you need to somehow predict where a dart is going to land with a typical throw from regulation distance. And you have about 200 milliseconds to do that. And then second, you need to somehow move the board to that predicted location. You have about another 200 milliseconds to do that. So let's start with the first part about how we predict where the dart is going to land. So the real secret here is that our dart has these tiny retro reflectors on it, and then we have a Vicon motion capture system. As humans, we can see in 3D because we have 2 eyes, and our brain calculates the difference between the 2 images and then tells us how far or close things are. This is why if you close one eye, you instantly lose that depth of perception. So that's basically what we're doing here, except we have 6 eyes all around the room, and each of these eyes, or cameras, can take a 4K resolution picture 260 times per second. But since it's hard to visually separate something so small moving so fast in front of a busy background, they actually use IR. So they blast out IR from all these IR LEDs, and then it hits the retroreflectors and then bounces back to the lens. So when I wave the dart around like this is what you and I see, but the motion capture system just sees a solitary dart floating around. One of the reasons this board took us so long to build was that for the first 2 years we were trying to make our own motion capture system. So we had our own cameras and one of these awesome NVIDIA TX1 boards, which is basically like a Raspberry Pi on Russian steroids. But it turns out it's a super complex problem to solve, and the Vicon system was just turnkey. So now that we have the XYZ position of the dart as it travels through the air, we use some MATLAB code to then predict where it will land. And the trick here is that anything you throw into the air, neglecting air resistance, will travel in a perfect parabola. Even something you wouldn't think of, like a high jumper, if you track their center of mass, it actually follows a perfect parabola shape. So we used our understanding of parabolas, and from a side view, we use that to predict the final up and down position of the board. And then to predict the final left-right position of the board, we know from a bottom view, a dart will follow a linear path. So we use good old y equals mx plus b, and the y-intercept, or b in this case, tells you how far to move it left and right for the final position. exactly where to move, let's talk about how we actually do it. So the board itself is on
The rest of this is
two
kinda
linear
interesting.
sliders, which
When they
allows
talk
us to
about the system they
translate
put it
in a
on.
specific location. So that provides the track.
I don't know, if you wanna watch the rest of it, you can ask me about that. I just put in here dartboard bullseye every time, if you wanna watch the rest of it. Obviously, I'm only interested in the math. Huh? Everywhere? So, I mean, the reason I wanted to show you that is, I thought it was a really decent illustration of a very basic use of equations. Now, I know the parabola stuff is in our future still, right? So, but you all know the trajectory of a basketball or something. When you throw it up, it follows this upside down U shape, right? So later we are going to talk a little bit about the equations that govern this shape, right? So the thing about mathematics is, if I know the equation that governs something, I can predict what's going to happen, sort of like what this is going on. So if you can see elements of its trajectory, you can use the equations to predict where it's going to be, and that's when it moves the dartboard. So that's part of what we're doing. We're just learning the basics of equations, but this is kind of like one thing that you can use it for. Now, if you think about something a little less silly than dartboard, is like intercepting missiles, right? So you have a missile coming in, you can see its trajectory, you shoot off your interceptor missiles, and they are based on the math behind what this guy looks to be doing. If this guy moves a little bit, this guy's got to know it, they got to change their equations, it's going to alter its flight path. But they're all based on equations such as the ones we're learning right now, right? And they all have to do, in this case it would be like a 3D kind of thing, but it's really the same idea. I want these two to intersect so that this blows up. It doesn't hurt anybody. Okay, maybe. Yeah. So, the next piece I kind of want to focus on, he said a couple things that's in our future, but I was cool with that. Y equals mx plus b was one of them. That should sound familiar to a few of you guys, if not most of you. But that's still kind of in our future. The other thing is, of course, he mentioned the intercept, right, which is where it was going to hit the area where the dartboard was, so it knows where to move this way, right? Like I said, he talked a little bit about the parabola, which is in our future, so we're not going to worry about that piece. I want to focus right now on the intercept piece. Maybe I should put you over here. Let's see. Okay. So we did barely touch on this on the handout, but I want to specifically, holy crap, I got